Um, well, welcome everyone to the Astronomy Colloquium. Unfortunately, the speaker though he had every desire to come, family situation, he couldn't make it at the last minute. So we're doing the next best thing, which is a talk via Zoom. Today's speaker is Edo Berger. He's a professor in the astronomy department at Harvard. Edo's primary interests are in time domain astronomy, particularly the study of gamma ray bursts, tidal disruption events, and peculiarly the study of substellar objects, particularly magnetism in brown dwarfs. After finishing the required military service in Israel, Edo studied undergraduate physics at UCLA and then joined our astronomy program in 1999. He graduated in 2004, went off to Carnegie Observatory as a Hubble Fellow, and thereafter joined the astronomy department at Harvard and in 2008, and rapidly rose to the position of a full professor. Edo is very well known for his seminal contributions to the field of gamma ray bursts and their connection to neutron star coalescence. In what I can only describe as a sustained and steady program, Edo and his students laid down a rigorous and comprehensive program aimed at understanding the origins and the workings of short, hard gamma ray bursts. This sustained investment paid off handsomely in 2017 when the first binary neutron star coalescence was discovered by LIGO and Virgo, and a weak gamma ray burst signal was seen with Fermi. Edo has trained and supervised a number of students who have gone off to successful careers in astronomy. So let me take you back, since he's from our department, to 1999, when Edo joined the department. It was a very vibrant period in 1997, thanks to the Keck Observatory and Beppo Sachs. We were able to show that gamma ray bursts were actually extragalactic. In 1999, I think Josh Bloom was in residence as a grad student, Titas Kalama as a postdoc, and Raim Sari was a postdoc, maybe transitioning to faculty, maybe a year later. Edo expressed a desire to work with me. Since I'm somewhat familiar with the Israeli system, I asked him which division he worked for during his compulsory military service. He informed me that was in the armed forces. I was a bit concerned, since the best students are usually sent off to the intelligence bureau. In any case, he looked earnest, and I have a very soft spot for enthusiastic people. Dale Frail and I had discovered radio afterglows just a year before from GRB, so I shipped Edo off to Socorro for the interferometry summer school so that he could learn radio astronomy. As was my custom then, the plan was for Edo to stay in sunny Socorro over the summer and learn observational radio astronomy from Dale Frail. During the summer school, the students are given a certain couple of observing time at the end of the school. Edo led a program of looking at a brown dwarfs which had shown X-ray, flare with Chandra, and that paid off handsomely because during those 2 hours, he detected radio emission. So he, with perhaps Dale's help a bit, the class under the leadership of Edo wrote a paper to Nature on basically showing that magnetism exists in brown dwarfs, and radio is a great way to probe, and that explains his long interest in substellar objects. After that, of course, when he came back, I had no choice. I had to take Edo, and that turned out to be a very good move because he became, as you can see, a very successful astronomer. But just in case all this praise gets to his head, I have to tell you another story. In those days, we'd actually go observing to Hawaii. This was at Waimea, though. And I'd go with the students, and many times I'd stop by in Manoa just so that the students could network and meet the astronomers. So when we finished our run, went off to Manoa, and we're renting a car at the airport in Honolulu. I saw a really nice yellow convertible, and I had some Hertz points. So I said, it'll be a fun thing. He's a young guy. So I asked them, hey, can I use some points and upgrade and get for the same, without paying more money, the convertible? And I told Edo, you can have the convertible. I've seen enough of Honolulu and go off for the evening and all that. And so first he started, we drove to the hotel, then I gave him the keys. And then I think the plan was that we'd go out somewhere and have dinner. And then he'd go for a long drive around, maybe in Diamond Head or something. When backing out of this spacious garage, Edo managed to scrape completely one side of the car. I then asked him, hey, what exactly did you do in the Army? He said, well, he was in the infantry, he was in the tank division. I said, this is not a tank. Anyway, when we returned the car, I sort of parked it so that they couldn't see the other side of the car. We signed out and quietly slipped away, taking a plane to LA. As far as I know, nothing happened after this. New car that was completely damaged on the left side. Anyway, so you can see Edo is also a very daring person, a bit given to being rash and full of energy. So today he's going to tell us something very different, which is how to apply machine learning for astronomy. All yours, Edo.
Thank you, Sri. Thanks for bringing back those amazing memories of totaling a brand new car with, I think it had 25 or 30 miles on it. But
that's right.
Yeah. So first of all, thank you for the invitation to give a colloquium, and I really wanted to do it in person. It would have been great to come and visit, and Caltech has a very dear place in my heart after spending 5 years there and having a really great time as a graduate student. But this is second best. So today, what I want to focus on is the development and use of machine learning in the study of astrophysical explosions. This is an area with quite a lot of activity over the past few years. But what I want to highlight today are innovative approaches that we've developed that leverage the use of real data rather than simulated observations, which is essentially what's done in most other similar projects. And also to take into account our physical understanding of supernovae, in particular, as we've developed it over the past several decades. And use that to explore a range of approaches that work better in some context versus others. So it's not just about finding some really cool algorithm that uses some spiffy new methodology, but it's really about what's going to work with practical situations and with real data. So that's the algorithms part, but I also want to show you today examples of how we are already using these approaches to enable new scientific investigations and to pave the way for science in the Rubin Observatory LSST era. So the work that I'll be discussing is an ongoing collaboration with several former and current students and postdocs, including a highly talented undergraduate student, Brian Su, who is going to be applying for graduate schools in the fall. So keep an eye out for him. I also want to highlight that this work is partially performed in my role as senior investigator in IFI, which is the Institute for Artificial Intelligence and Fundamental Interactions, which is one of the inaugural cohort of NSF AI institutes that's been running for the past 2 years. And it's also supported by the NSF Computational and Data-Enabled Science and Engineering Program and the Harvard Data Science Initiative. So with that, here's a quick outline of what I will try to cover today. So I want to start with a brief motivation of supernova and time domain science and a quick overview of how we classify supernovae and motivate the need for photometric classification and the need for multiple approaches, or at least exploring multiple approaches. I will then discuss our new approaches that we've developed for what I will call broad supernova classification. So this is classification of all types of supernovae into their different categories. And I'll talk about the advantages and disadvantages of this approach and provide an example of application to a specific type of supernovae called superluminous supernovae. And then I'll switch gears and discuss a complementary approach of targeted classification, specifically in the context of rare transients, such as superluminous supernovae and tidal disruption events, and how this approach led to an interesting new category that we've been calling luminous supernovae. Okay, so to motivate supernova science broadly, supernova really sit in the center of a wide range of astrophysical investigations. They are the endpoint of stellar evolution, specifically of massive stars and massive stars in binaries. And so the properties of supernovae can teach us about these phases of stellar evolution that are very difficult to simulate. These are very short, the final few, sometimes days, and in the life of these massive stars. Supernovae also give birth to exotic compact objects, such as neutron stars and magnetars and black holes. And there's an interesting interplay there because these compact objects can also influence the nature and the appearance and the properties of supernovae. Now, sometimes these compact objects are born in pairs coming from binary massive stars, and those sources eventually become gravitational wave events that are now being detected by LIGO and Virgo. Supernovae also play a role in feedback in galaxies and have an impact on the interstellar medium in galaxies, on star formation, quenching it, and also, of course, play a role in nucleosynthesis. So supernovae and their progenies as compact object mergers give rise to nearly 3/4 of the periodic table. And finally, some type of supernovae, specifically the type 1As, which are standardizable, can be used to measure the expansion rate of the universe and therefore its composition. So supernovae sit at the center of many areas of astrophysics. And that gives us a motivation for wanting to advance our understanding of these events. Now, when we talk about supernovae, there are different types of data that we can work with. So we have images of the supernovae themselves, as well as their context in which they occur, their host galaxies. If they're nearby enough, we can identify specific stellar populations that they're associated with. And I'll come back to this later. We have light curves, which are essentially the brightness evolution as a function of time in different filters, different part of the electromagnetic spectrum. And we have spectra, which tell us about the chemical composition of the explosion, as well as its kinematic expansion velocity and its evolution. Now, spectra also are used to classify supernovae into different categories. So our classification system of supernova relies on the availability of spectroscopy. And in its most simple form, it is based on the appearance or absence of several key elements. So in particular, whether the supernova spectra contain hydrogen or not. If they do, it's a type 2. If they don't, it's a type 1. Whether they contain strong silicon, which will make a type 1A. Or if not, whether helium is present, which will classify the supernova as a type 1B. Or if there's no hydrogen or silicon or helium, then we call them a type 1C. So this is a basic classification scheme that's been around for a long time. With the advent of larger and larger surveys, it's become possible to find events that don't exactly fit into this classification scheme. And so things have been getting a bit more complicated over the last decade or so, with some events that might show hydrogen in some phases of evolution, but then the hydrogen disappears or appears. In some cases, the hydrogen is in the form of narrow lines. And in some cases, these supernovae have particularly broad lined or associated with gamma ray bursts. But in any case, in all of these types of events, we rely on spectroscopy to classify supernovae. Now, it turns out that this classification, which is very much just based on, as I mentioned, the appearance of specific lines, actually nicely maps onto physical properties of the progenitors of different types of supernovae and the explosion physics. And so we know that type 1A supernovae come from the explosions of carbon-oxygen cores. It's not clear if, carbon-oxygen white dwarfs, whether they're in binary white dwarf systems or with a main sequence or evolved companion. Whereas the type 2 and 1B and 1C come from core collapse explosions of massive stars, with a difference in the spectroscopic appearance being attributed to whether they retain their hydrogen envelopes in the case of type 2 supernovae that come from red supergiants, or whether they lost their hydrogen as well as helium envelopes in the case of type 1Bs and 1Cs. Now, the discovery rate of supernovae over the past 120 years or so, or I guess coming up on 140 years, has increased dramatically. And so the first extragalactic supernova was discovered in 1885 in Andromeda. Currently, predominantly thanks to ZTF, the discovery rate is now over 10,000 supernovae per year. And in about 2 years or so, with the advent of Rubin Observatory and the LSST survey, we anticipate a discovery rate of more than 1 million supernovae per year. So this is fantastic for advancing supernova science, but of course it comes with other challenges. And one of the challenges is that the classification rate of supernovae has actually been steadily dropping. So at the present, spectroscopic classification is only at a level of about 10%. And that requires quite a massive effort with a wide range of telescopes all over the world and significant programs that takes tens or even hundreds of nights on telescopes that are 2 meter or even larger. And so in a sense, the classification of the spectroscopic classification of supernovae is at the present is more or less what we can anticipate going forward, which means that as the discovery rate increases by a factor of 100, the classification rate will drop by a factor of 100, or the classification fraction. So for Rubin Observatory and LSST, we anticipate that only 1 in 1,000 supernovae or so are going to be spectroscopically classified. So that raises several key questions that we're already grappling with presently, which is, how do we decide which supernovae, which transients to follow up with expensive spectroscopy and multi-wavelength observations? How do we manage to advance supernova science, given its impact on so many other areas of astrophysics, without throwing away 99.9% of the data set? And how do we actually enable the discovery of new types of transients and new types of supernovae as we increase the discovery rate and have the potential to find events that are too rare to be found in current surveys? So those are the questions that I'm going to address today. So the hope is that we can do this using what's called photometric classification. So the motivating question is, can supernovae be classified solely based on their light curves, on their brightness evolution as a function of time in different filters? And mainly using survey data. So we actually use the data that will come either from ZTF or from LSST in the future without the need for spectroscopic follow-up. So this answer to this is quite complicated. So type 1a supernovae are mostly homogeneous, which is why they're used as standardizable candles. But core collapse supernovae are not. So you can see in the image on the left that we can standardize type 1a supernovae. They, to begin with, span quite a narrow range in terms of their luminosities and light curve shapes, as well as colors, and they can be standardized. But core collapse supernovae appear in a wide range of luminosities, time scales, color evolution that might make it quite difficult to classify them. Now, because type 1a supernovae are homogeneous and because they can be used for cosmology, most of the efforts on photometric classification so far have focused on kind of binary classification. So asking the question, is a supernova a type 1a or not a type 1a, rather than is it a type 1a or a 1b or a 1c or a 2n or a 2p and so on. And that problem is somewhat easier to solve than if we want to classify all types of supernovae. Now, there's another complicating factor, which is that different supernova classes have a wide range of observed rates. So I'm showing here a couple of figures from the Lick Observatory Supernova Survey, showing their volume limited and magnitude limited breakdown of the 3 basic supernova types, type 1a, 1b, c, and type 2. And a much more recent example from the ZTF Bright Transient Survey, which shows that similar diagram, but going into all the different kinds of more rare types of supernovae and other optical transients. And the bottom line here is that we have quite a broad range in magnitude limited surveys, which is what all these surveys are, all the way from about 70% of the population being type 1As to transients such as superluminous supernovae and tidal disruption events, which are 1 in 100 or 1 in a few hundred. So this also raises two important points. One is that a classifier has to perform, or at least for type 1A supernovae, has to perform better than about 70%. And I was recently actually attended a talk where somebody was talking about a classification algorithm that they produced, and they were very excited because with only a few data points, it could classify type 1A supernovae with a purity of about 70%. And I pointed out that actually with a single data point, I can also classify type 1A supernovae with a purity of 70% by simply calling every supernova a type 1A supernova. And then, that classifier will be right 70% of the time. So if we want to exceed that basic level of classification, then we need to have classifiers that perform much better than this. But the other point here is that since we're looking at supernovae that have a range of about 2 orders of magnitude in observed rates, a single approach to classification might actually not work best. Okay, so that motivates kind of that what I talked about at the beginning and what I'll be talking about for the rest of the talk of different approaches to classifying supernovae. Okay, so let me jump into the first type of classifiers. These are classifiers that are designed for broad classification of supernovae. So trying to take all of this complexity and trying to classify these transients into the different types that we know about. So when we embarked on this project, one thing we decided to do was to work with real data. And we were motivated with the notion of applying this classification down the road with LSST. And so we wanted to work with a data set, one that we had access to, and two that was as similar to LSST as possible. And so we used the PanSTARRS medium deep survey. So for those who are not familiar, the PanSTARRS 1 medium deep survey covered 10 fields. Each one is 7 square degrees in 4 different filters, G, R, I, and Z, and with a cadence of about 3 days. And the magnitude limit per visit was about 23.5. So it's about 1 magnitude shallower than what LSST will produce. And with this survey, we discovered about 1,000 supernovae per year. So we've been calling it a milli LSST, since LSST will find about a million of them per year. So of these 5,000, we classified about 10%, which, as I mentioned, is kind of the state of the field at present. And you can see the breakdown here, the majority of them type 1A and type 2s, but also a sizable number of type 2N and 1BC and superluminous supernovae. And this is kind of a representative example of what the data set looks like. So we have data in 4 filters. Green is G, then red is R, purple is I, and yellow is Z. And these are 2 different spectroscopically classified supernovae, a type 2 and a type 1B or 1C. Okay, so this is the data set that we're going to be using. And the first classifier that I'll talk about is called SuperPhote. Okay, so SuperPhote is the first machine learning based classifier that's been trained and evaluated with real data and using multiple supernova classes. So prior to this classifier, people have been doing things either with simulated data or using real data, but classifying, only using a binary classification of 1A versus not 1A. Okay, so how does this classifier work? So it essentially has two parts to it. The first one is that we fit each light curve in each band independently using Markov chain Monte Carlo with a flexible analytical model that's designed to capture the diverse shape of supernova light curves and then extract parameters that can be used in the classification. So what I'm showing here are examples of a type 2P and a type 1A light curve. And the model, the black line is our model. So as you can see, it can fit the shape of a type 2p that has a plateau. It can fit the shape of a type 1a that has roughly an exponential rise, exponential decline. And it does much better in this context than previous models that have been used to just do binary classification of 1a versus not 1a, which are shown in blue and yellow. Now, what's nice about this particular model, one key advantage of it, or two advantages, is one, the parameters are easily understood. So we fit for things like the amplitude, the brightness, the duration, the rise time, the decline time, the duration of the plateau, the slope of the plateau, and so on, the color. So these are parameters that are easy to interpret when we're doing classification. And another important point here is because we're using MCMC to fit the light curves, we can also carry through the uncertainties on the model parameters that we're using for classification and translate those to an uncertainty on the classification itself. So those are the advantages of this approach. The disadvantage is that the model still is relatively simple. So it may miss some subtle effects in the data that we're not clearly aware of. And we're not using K corrections. So predominantly because K corrections depend on the type of supernova, and we don't know the supernova type a priori. It's something we're trying to figure out. It's actually hard to incorporate K corrections. So that means that the model is, again, somewhat simplified. And because we're using supernovae over a wide range of redshifts, it creates a certain level of fuzziness in the classification that could be improved in the future if we figure out how to do this. Okay, so here are examples of light curves modeled with this particular model that I just described. And you can see that the data quality varies from one supernova to another, whether we have a rise, a decline, but the models overall do a good job at capturing this broad range of behavior that we see in these supernovae. Okay, so once we have all of these parameters that come from the model, then we can use them for classification. So here's an example of 2 out of several parameters. So we're looking at absolute magnitude on the y-axis and the duration defined in some particular way on the x-axis in the 4 different filters, G, R, I, and Z. And you can see several interesting things here. So just to orient you, the green points are type 1a supernovae. You can see that those are well clustered. That again points to the uniformity of type 1as. They sit in a very specific part of parameter space. The blue ones are type 2. The red ones are 1b and 1cs. And you can already see that in all of these different filters, the 1Bs and 1Cs overlap in this particular subset of the parameters. They overlap significantly with the type 1As and the type 2s, which is going to create some complication in how we separate them. The purple ones are type 2N, and the yellow ones are superluminous supernovae. Now, the other thing you can see in this plot, in addition to the fact that some classes of supernovae separate well from others and some overlap, is that there are very different numbers. And that goes back to the fact that we're using a magnitude limited data set. So the majority of our sources are type 1a supernovae, and the rest of them are less and less common. So when it comes to classification, we don't want to end up in a situation where the classifier will essentially classify almost everything as type 1a, because that's the majority of sources. So we have to resample the population. And so here's again an example of the original data set in some parameter space of feature 1 versus feature 2. And what we do is we oversample the minority classes, and we try 2 different approaches, something called Gaussian resampling, which essentially uses the fits the population in this multidimensional feature space with a Gaussian, and then resamples fake events from that distribution, or a different one called synthetic minority oversampling technique, SMOTE, which does the same thing, but in a somewhat different way. Okay, so what we've done in this with Superphot is that we've tried a lot of different algorithms using essentially different types of extracted features. So we either we use features directly from the model, or we use other features that are derived from those, and so on. So we have 4 different sets of extracted features. We have the 2 different versions of data augmentation, and we tried 3 different types of classification algorithms. Something called support vector machines, random forests, and a very simple neural network. And the goal was to just explore and see how these different approaches with different sets of features perform. So these 2 tables here show completeness in the top one and purity in the bottom one. And then the different rows are different types of supernovae, and the different columns are the different combinations of features and data augmentation and classification algorithms. So obviously, I don't want you to absorb all of this, but I think there are kind of 2 key things that can be taken from here. So blue is good. Blue means that the purity is high and the completeness is high. Red is bad. That means the completeness is low and the purity is low. So you can see that systematically, while there are variations across these different combinations of algorithms, there are some trends that are easy to see in the data, which is, generally speaking, we can classify type 1a supernovae well with high purity and high completeness, and that is due to their uniformity. We do really poorly on type 1b and 1c supernovae, both in terms of purity and completeness. And that predominantly has to do with the fact that they overlap significantly with type 1a supernovae in terms of their properties. And we can do well on some fairly rare types of supernovae, specifically the superluminous supernovae and type 2Ns. And again, that's because even though they're relatively rare, they stand out in terms of their properties from the larger populations of type 1a and type 2s. So what I'm showing here are what's called the confusion matrices. So we have the true label on the y-axis and the predicted label on the x-axis. And for a classifier that's performing well, we want to see the diagonal part of the matrix highlighted. And you can see that that's indeed the case. And the classification success rate for our best combination of classifications is somewhere in the range of about 60, 70% for the type 1 BCs at the low end to about 90% for type 1a supernovae. So the nice thing is that this actually outperforms classifiers that are trained on simulated data. And the range of success in classification reflects both the inherent difficulty of classifying some supernovae as opposed to other, as well as things related to data quality. So what I'm showing here is a kind of a nice visual of, for the different classes, just of all the events that were classified as a specific class and sorted by the classification confidence. So the events on the left side of the plot have a low classification confidence, and the events on the right side of the plot have a high classification confidence. And so if you look in the second row from the bottom, the type 1a supernovae, you can see that most of the events that were misclassified as type 1a, so they are spectroscopically something else, but they were classified as type 1as, have been classified as such with low classification confidence. Okay, so that's that predominantly has to do with data quality. So these are events with poor sampling of the light curve, perhaps the rise or the decline are missing. And so they're misclassified, but the classification confidence to begin with is very low. So they can be discarded. But you can also see in other cases that there are some events that are misclassified, but with very high confidence. So it might be a type 1c supernova that's classified as a type 1a supernova with 100% classification confidence. And that has to do with fairly well understood, I think, cases. So some of these well-sampled events that I'm showing here that are misclassified with a high confidence are, for example, type 2 supernovae that have a very short plateau or no plateau at all, what used to be called type 2L supernovae, that can get confused with type 1Bs and 1Cs, or type 1As that have significant dust extinction and therefore have a low luminosity, so they get interpreted as, again, type 1Bs or 1Cs, or particularly luminous type 1Bs and Cs that might appear to be type 1As. So I guess the main takeaway here is that even when we have high data quality, there are going to be misclassifications that have to do with overlap in feature space. Okay, so following on this approach, we have also been exploring a somewhat different approach. So this is a model independent. So in the previous, in Superphot, we impose a specific model and we use the features of the model to classify the supernovae, and we can only train the classifier with events that are already spectroscopically classified. So this next algorithm called SuperRain takes a different approach. So it's model independent. We don't impose a specific analytical form to extract features from the light curves. And it's also semi-supervised, which means that we can use both classified and unclassified events that the neural network can actually learn from. So instead of just using 500 supernovae to train the neural network, we're using both the unclassified and classified events. And here we've used a subset where we've added 1,800 supernovae for which we measured redshifts from host galaxies. So in this classifier, as well as in the previous one, we do need to know the redshift. So what we do here is we use Gaussian processes to fit the light curve. So instead of imposing some specific analytical models, we use Gaussian processes. Then we use something called a recurrent autoencoder neural network to learn a simple encoded version of these modeled light curves down to something like 10 features. And then we use a random forest classifier with those 10 features from the full sample of 2,300 supernovae, but then verified and trained on the subset of 500 spectroscopically classified ones. So I don't want to go into a lot of the details here, but what we can do then is take a variety of these events. So these are events where we have a redshift from a host galaxy, but we don't have a spectrum of the supernova, so we don't know the type. And for each one of these events, we can generate probabilities of what the supernova is. And we can generate a probability into these 5 categories that we've been using. So some of these will have very high probability, 98% of being something. In some cases, it might be 20% of this and 20% of that and 20% of the other one, all adding up to 100%. So we've done the same kind of evaluations. So these are, again, confusion matrices for completeness and purity. And we find overall very similar results. So the classification success rate is relatively low for the type 1Bs and 1Cs, around 35, 40%. And it's very high, around 95% for type 1A supernovae. Okay, so what are the key lessons that we've learned from this broad supernova classification? So the classification success rates depend somewhat on what methodology is used, what type of algorithm, what kind of approach, what kind of feature extraction we're using. But it can be as high as 90 or 95% for type 1A supernovae and superluminous supernovae. And that has to do with the uniformity of the type 1As and with the fact that superluminous supernovae really stand out in their properties from the rest of the population. And it's the lowest for the type 1B C supernovae, predominantly because they overlap in feature space with both type 1As and some type 2s. The classification to work with any level of success requires a redshift. So that is a challenge. Our hope is that for LSST supernovae, that a substantial fraction of them will have photometric redshifts from their host galaxies. The model-based approach, where we fit an analytical model, is more easily interpretable, but it makes some simplifying assumptions, whereas the autoencoder-based approach has the advantage that it can learn about the best way of distinguishing supernovae, both from classified and unclassified events, and without the supervision of a human. But it turns out that it performs similarly to the model-based classification. And then misclassifications are due both to poor data quality as well as intrinsic overlap in feature space between some supernova classes, and also because we're making some simplifications. We're not correcting for host galaxy extinction. We're not using K corrections. And one of the things we're testing now is using an image-based neural network on images of the host galaxies to generate additional features. So not just using the light curve information, but using the contextual information of where these galaxies, where these supernovae are happening. Okay, so I promised that I'll talk a little bit about applications. So I just want to quickly show you one application of this approach, which is the first study of photometrically classified superluminous supernovae. So in this recent paper from earlier this year, we took the output of these classifiers and we took all of the photometrically classified superluminous supernovae from both superphot and superrain, and we looked at how to construct a robust sample of events, then how to model them in the same way that we model the spectroscopically classified events, and then compare the two populations, the spectroscopically classified and photometrically classified superluminous supernovae. So we started with a population of about 67 events that were classified as superluminous supernovae, or superluminous supernova was essentially the highest confidence classification out of these two classifiers. One thing we found right away is that some of these events suspiciously landed right at the nucleus of galaxies that, based on our spectra of these galaxies, are AGN. And so it turns out that even though we tried to limit our sample to just supernovae, there were some large AGN flares that creeped into the data. And because AGN flares was not a category in our classification, those tended to get classified as superluminous supernovae. So we're able to clean those out. And then we experimented. We can change the classification confidence thresholds, how many data points we want. So those are things we can play with that are shown here on in this matrix, and we can dial the sample size higher or lower depending on our needs. Of course, the higher the minimum confidence and the larger the number of data points, the more robust the sample is going to be, but the sample size is also going to decline quite dramatically. So we settled on a classification confidence greater than 0.5 and greater than 11 detections across the 4 filters. And then we modeled these events, and so we end up with a sample of 20 photometrically classified superluminous supernovae. So we had to throw away about 65% of the initial sample, but I think this allows us to construct a more robust data set. Okay, so once we have that, then we model the light curve. And here I wanted to take a break for a minute and just advertise this really incredible tool that I think quite a lot of people have been adopting over the last few years, called MOSFET, that we've developed about 4 years ago now. So MOSFET is the modular open source fitter for transients. And it's a really nice platform for rapidly modeling different types of transients using simplified analytical model, which works on multi-band data and provides robust uncertainties on the resulting parameters. So the idea here is that we take our data and then we have this modular system where we can plug in different energy sources. So it could be radioactive decay of nickel-56, or it could be CSM interaction with a circumstellar medium. It could be a magnetar, a spin-down energy of a magnetar. It could be a radioactive decay of our process elements. It could be accretion onto a black hole. It doesn't matter. All of these models are built in. And then we couple that to simple photon diffusion and spectral energy distribution, extinction, iteratively fit the data and get a sense of what the best fit parameters are. So here for this particular case, we're using the model that's been favored for the interpretation of superluminous supernovae, which is spin down energy from a millisecond magnetar. Okay, so on the left-hand side, I'm showing the light curves and the fits from MOSFET for the photometrically classified superluminous supernovae, all 19 of them. On the right-hand side, I'm showing the peak absolute magnitude in G-band as a function of redshift. And here I'm showing in the solid squares the photometric events, and the open circles are the spectroscopically classified events. And one thing you can see right away is that the photometrically classified events, as might be expected, generally tend to be at any given redshift systematically less luminous than the spectroscopically classified events. And that's because when we chose objects for spectroscopic follow-up, we tended to choose the brightest objects. And with photometric classification, we can dig deeper into the population, and we're not limited by the capabilities of spectroscopic follow-up. So what I'm showing here are plots of parameters that come from the modeling. And so it's things like the spin of the magnetar, its magnetic field, the ejecta mass, the ejecta velocity. And the point to take away here is that once we model the spectroscopic and photometric samples in the same way, we find that they're statistically indistinguishable in terms of the model parameters. So that gives us confidence that this photometrically classified sample really is drawn from the same population as the spectroscopic events. And in fact, we find that the photometric sample exhibits the same correlations that are seen in the spectroscopic sample. And unfortunately, I don't have time to go into this, but these correlations between things like the magnetic field and the spin, or between the ejecta mass and the spin, actually seem to be fundamental to how these progenitor stars evolve and end up as progenitors of superluminous supernovae. So this initial study has a sample of only 20 photometrically classified superluminous supernovae. The spectroscopic sample is about 100. So this is just a proof of concept, but with LSST, we will be able to perform this analysis during the 10-year of the survey. We anticipate to produce a sample of about 10 to the 5 superluminous supernovae. So then the photometric sample will be the predominant one. Okay, so in the last few minutes, let me switch gears and talk about targeted classification. And this is a project that we've called FLEET, standing for Finding Luminous and Exotic Extragalactic Transients. And so it's motivated by the basic fact that this broad classification that I've talked about so far inevitably results in compromises that work well for the majority classes, for the common types of supernovae, like type 1a supernovae, but may not work so well for the rare kind of needles in the haystack, like superluminous supernovae. And also the approaches I showed you before are approaches that use the entire light curve. So that means that we're classifying things after the fact, after a supernova has already happened and faded away and disappeared. And so we can use those to construct photometric samples, but it's hard to use them for real-time follow-up. So what FLEET does is it's the first targeted classifier that's been devised, and it's the first classifier that uses both light curve and contextual information. So the goal of this classifier is very simple and straightforward. It's to rapidly identify superluminous supernovae with high confidence for spectroscopic follow-up or for follow-up with the VLA or ALMA or Chandra. So, so we don't want to, it's a case where the sample in random selection of superluminous supernovae from a data stream from any survey, whether it's PennSTARRS or ZTF or in the future LSST, will only have a classification success rate of 1.5%. And we don't want to waste a lot of telescope time chasing after this 1.5%. So again, the goal here is to take this pie chart where superluminous supernovae are 1.5% and turn it into a pie chart where they're 85%. So the goal is to classify superluminous supernovae at the expense of all other transients. We focus on purity rather than completeness, focus on rapid identification at the expense of model complexity, and trying to identify things early rather than after the supernova has faded away. So how do we do this in practice? We essentially, in real time, retrieve every supernova that's discovered in any of the ongoing surveys, predominantly ZTF, but also Atlas and others. So that's about 50 to 70 supernovae per night currently. And we use archival imaging, mainly the Pan-STARRS 3Pi data, to determine first the host galaxy association for each one of these supernovae. So the first thing we do is we use a custom classifier to separate stars and galaxies, which is easy to do when things are bright, but not so trivial when objects are faint. We reject the stars, we identify and keep all the galaxies. We then use the probability of chance coincidence of each one of these galaxies to probabilistically associate each supernova to a host galaxy. And then we extract the properties of the host galaxy, its size, its brightness, its colors, the offset between the supernova and the galaxy. And most importantly, we don't require a redshift for any of this. So unlike the previous classifiers, here we don't actually rely on having knowledge of the redshift in advance. So that's the contextual information, the galaxy information. And then we use the light curves. So we fit the light curves with a very simple model. And we extract very basic properties: the peak brightness, the width of the light curve, and its asymmetry, essentially 3 parameters, which we can do very rapidly for 50 to 70 events per night. So for the main classifier, we only use the first 20 days of data to enable rapid spectroscopic and multi-wavelength follow-up. But I'll show in a minute, we also trained classifier versions that use the entire light curve, or that use redshift in case photometric redshift is available. Okay, so finally, we have a set of features that come from the light curves, and we have a set of features that come from the galaxy. And we just use a simple random forest classifier trained on a sample of about 1,800 spectroscopically classified transients that are publicly available in the literature from a variety of surveys. And using this, we can assign a probability of being a superluminous supernova for each event. Okay, so how does this perform? So what I'm showing here on the left side is the completeness as a function of this probability of being a superluminous supernova. And on the right-hand side is the purity. And if you look first at the yellow curve, then you can see that the peak purity that we can achieve with this approach is about 80%. So 80% of the time, we can correctly identify a superluminous supernova based on these combination of features of the light curve and host galaxy, which is a factor of 50 improvement compared to random selection, which would give us only 1.5% success rate if we were randomly classifying these. So that's a substantial improvement in classification. The price we pay is that the completeness is only about 25%. So we miss about 75% of the events. But as I mentioned, we care more with this approach about purity than about completeness. So in practice, this means that if we have about 1,500 supernovae discovered per month from various surveys, ZTF predominantly, that means that 23 of these 1,500 will be superluminous supernovae. That's the 1.5%. Then we can identify 6 candidates per month. That's the 25% completeness. And then correctly spectroscopically identify 5 superluminous supernovae per month. So that's the 80% purity. So 5 events per month, that's about 60 per year. And so that means that within a couple of years, we can double the number of spectroscopically classified superluminous supernovae, which is not bad because it took about a decade to get to 100. And with LSST, we'll scale this up to about 2,000 events per year. Now, if we do use additional information like redshift, or we use the entire light curve rather than just the rising part of the light curve, then the purity is similar, but the completeness rises up to about 40 to 50%. So we can recover more events. So this was our training of the algorithm. So now we've been running it for about 1.5 years or 2, of course, during the pandemic. So lots of gaps in the data and so on. But in the past 2 years, there have been 38 superluminous supernovae classified spectroscopically worldwide. And our fleet algorithm is responsible for classifying 21 of them. So fleet followed up by classification with telescopes like Magellan and MMT. So we've been responsible for more than half of all classifications. And it turns out that the classification statistics, when we're actually using this in real time, work actually better than expected. So for events that have a classification confidence of greater than 50%, the completeness is about 40% as opposed to about 25 or 30% that was predicted. The purity is about 80% compared to about 50%. And the classifier, the late time classifier completeness is actually similar to what we anticipated. But this actually works in practice better than we anticipated. Okay, so given this success, we're now developing a version of the same approach focused on tidal disruption events, which is another rare class of transients. And here too, we're using a combination of galaxy properties and properties of the light curves. So what's shown here is a plot of on the x-axis, the G minus R color from the light curve. And on the y-axis is the offset between the transient and its center of its host galaxy. And the yellow events are the tidal disruption events. And you can see that they tend to be blue and occur at the centers of their galaxies. So those are the kind of features that allow us to separate them from other transients. So tidal disruption events in the current data sets are actually even more rare than superluminous supernovae. So only about 0.5% from based on the ZTF Bright Transient Survey, only 0.5% of all transients are tidal disruption events. But with this approach, if we focus on events that have a probability of being a TD of greater than 50%, we can actually achieve a purity of 30 to 40% and a completeness of almost 50%. So again, that's a improvement by about a factor of 70 in the success rate of the classifier. And if we look at even more strict cuts, so probability of an event being a TD greater than 80%, then we can achieve a purity as high as 80%, again, at the price of a lower completeness. Okay, so I think I'm running out of time. So let me just finish here. I wanted to show some examples that came out of this, but let me just throw up 3 key lessons from this targeted classification approach. So this approach can be tailored to specific types of rare events, especially ones that exhibit unique light curve or host galaxy properties. So things like very luminous events or ones that happen in the centers of their galaxies. But there are other types of rare transients where this can be applied. These fast blue optical transients and calcium-rich transients and other types of rare transients. Using the combination of light curve and host information increases the success rate. And the great thing about FLEET is that we've also found other types of interesting, rare, unique transients that were not part of the training set. So in general, it seems like when we start digging into these very rare transients, we find other rare transients that are equally interesting. Okay, so I'll skip this part and just leave the conclusions up, and I'm happy to take any questions you have.
Okay, well, please raise your hands in the Zoom, the reaction box, and I'll just manage the questions. Ilaria?
Hello. So I have a couple of questions. One is about the MOSFET fitting that you showed. I mean, if I am understanding, your classification is based on the shape of the light curve, and the MOSFET fit is based on the shape of the light curve. So is that surprising that you're finding the same correlation, or is that somewhat circular?
That's an interesting question. I think that there is some. I wouldn't say that it's exactly circular because superluminous supernova in general, as you can see from these slides, I'm not going to go back, but they span quite a broad range of properties in this multi-dimensional phase space of spin and magnetic field and ejecta mass. And you can imagine that we could have ended up in a different scenario where all of our photometrically classified events would only occupy some particular subset of that parameter space. So I think that it is true that both the classification and the modeling use the same data, which is light curves. But I don't think it's obvious that they would necessarily, the events that were classified would span the same range of properties or would necessarily show the same correlations that the spectroscopically classified data set shows.
Thanks. I also have another question, which is about the fleet. So you said that with LSST, you're going to scale up to 1,000 per year. Do you actually have the follow-up power to really classify 1,000 per year?
Yeah, I mean, look, right now we're classifying, and by we, I mean the community as a whole, is classifying of order 1,000 supernovae or a couple of thousand supernovae per year. So, you know, if we took those resources and we all agreed to study superluminous supernovae, then we can do it, or TDs. But I don't think we necessarily need to classify all of those. I think that we can also look at it from the perspective of building up large populations of sources that we can study without real-time spectroscopic follow-up.
Thank you.
Okay, Michael.
Hello, great talk. Yeah, so I was wondering, how much better do you do than the best non-machine learning based approaches for classifying supernovae?
Well, I'm not sure what you mean by non-machine learning based approaches. I mean, you know, I think that people who are experienced with supernova science can potentially look at light curves by eye, you know, one object at a time, and say, hey, I have a feeling that this is a type 1a, or this is a TD, and we should maybe get a spectrum of this. I think a lot of the work in the past has been that way, but it's not really scalable. I don't think it's scalable to where we are right now with about 10,000 supernovae discovered per year. And it's definitely not scalable to LSST, where it's going to be about 1 million supernovae per year. So I don't think you want people just looking at those light curves by eye and saying, hey, to me, this feels like a type 1a or a type 2. So I think that's really the power of this approach, is that you can automate this whole process, but first you have to convince yourself that it works. And also, I think the important part here that I tried to highlight, hopefully it came across, is that there are pitfalls here, and we need to be aware of those pitfalls. We don't want to trust these approaches blindly just because the computer science part of it is interesting. We want to use our knowledge of supernovae to try to understand when things work and why some classes of supernovae are going to be really hard to classify with these approaches. As I mentioned again and again, the type 1Bs and 1Cs are going to be really hard or really difficult to take out of the data.
Mm-hmm.
Thanks, Edo. There are a few other questions. So once your question is answered, please lower your hand. Mansi is next. Sorry, Ashish.
Thanks for the great talk, Edo. Right at the start, you mentioned how we'll be able to classify very few objects by the time of, say, LSST, when we are finding many, many faint ones. So in your machine learning thing, how much effort are you spending on transfer learning, seeing how we do for the fainter ones and whether your models can transfer to the fainter ones?
Yeah, I think that's a good question. So our spectroscopic sample goes to about magnitude 22 and a half. So and then our photometric sample, we're going down to about magnitude 23 and a half. So we haven't tested this rigorously, but my sense is that, you know, this one magnitude difference is not killing us. I think the part that's not 100% clear to me yet is how transferable this is from one survey to another. So can we take what we've trained out of the box and apply it to LSST? And so one of the things we're trying to do now is we're working with the Subaru Hyper Supreme Cam team to try to apply this to their events and compare it to what they find spectroscopically.
Thanks.
Okay, Mansi.
Hey, Edo. I'm delighted to hear that you're enjoying the ZTF stream. So let me just
Very
say
much.
that first. The question I had for you was regarding your targeted classification for the superluminous supernovae. Are you worried about the completeness being so low? Because the superluminous supernovae are actually the nicest, right? I mean, they have the unique long rise, very different from the rest of the zoo of supernovae. So are you worried the completeness is coming out to be in the 20s or something, 25 or something I saw?
No, not so much. And I think that the primary reason is that we're not using redshift. So I think in the, in the other, the kind of the classifiers that I talked about in the first part of the talk, we choose the full light curve and use a redshift. The completeness is much higher because once you have a redshift and you know the luminosity, then it's kind of game over. You can see that they stand out from the rest of the population. But here, because we don't want to rely on redshift, because in most cases, redshift information is not available, then it's really only the shape of the light curve and the properties of the host galaxy that give us a separation. And it turns out that, there are a lot of type 1a supernovae that sufficient number of them that have light curve shapes that are close enough. And because you don't know the absolute magnitude, then the completeness ends up being lower. But,
probably worth looking into a little bit more because it's actually, the long rise is very unique for these superluminous events. And internally, the ZTF team is having better luck and more numbers from the same stream. So
good. Yeah, I think it would be great to see a publication on that. Yeah,
it is on archive, February, the first 78. I can send you the links. The 2 papers.
Yeah.
Okay. Dale Frail gets the last question. Dale, all yours. Can't hear you.
Yeah. Again, lovely to see you, Edo, and a really great talk.
Thanks, Dale.
Going back into your fleet algorithm when you're focusing on that 1.5%. And so far you've used it to identify superluminous, supernovae, and tidal disruption events. So this might be a naive question, but let's say I'm kind of trying to look at this from the perspective of finding totally new phenomena, like outliers that don't belong in any of the classification schemes. Can I use something like Fleet to find that piece of phase space that just doesn't fit anything? Or is that kind of lumped into the others? Is this a tool for finding new phenomena?
Yeah, no, Dale, I think that's a great question. So that was one of the points I raised at the beginning of the talk, that one of the things we want to do with photometric classification is be able to discover new things, not just the things we know about. So Fleet actually practically has turned out to do that, but not in a systematic way. There's a whole other branch that I didn't talk about, which is just the whole concept of anomaly detection. So we had a paper a year ago that looked at this, where essentially we're using the output from this broad classification to look for things that fall out of the parameter space of the other events. So you look for anomalies essentially as things that are not the same as what your algorithm is trained to find. But it's not a trivial problem of how to discover new things in any of these approaches.
Okay, if any of you want to buy Edo's thesis, it's apparently available on Amazon for $22.52.
Trio, are you getting a cut of this from Amazon?
Anyway, thanks, Edo. So I think that's the end of the colloquium. Goodbye, everyone.
Thank you.